Table 19.2.311 in the 2025 edition of NFPA 13 provides default design area values for sprinkler system calculations, assuming a wet pipe system, standard response sprinklers, and a horizontal ceiling. But what if these conditions change? In this video, we'll examine how to adjust the design area for variations in ceiling slopes, system types, and other factors influencing hydraulic design. As expected, when a fire starts, quick response sprinklers activate faster than standard response sprinklers. This earlier activation helps contain the fire more quickly, limiting its spread to a smaller area. According to NFPA 13 2025 edition, the design area can be reduced, but only under specific conditions. This applies to wet pipe systems serving light or ordinary hazard occupancies, where the ceiling height is 20 feet or less. To qualify, there must be no unprotected ceiling pockets larger than 32 square feet and no unprotected spaces above cloud ceilings. When all the required conditions are met, the standard allows us to reduce the design area based on the ceiling height. This reduction is provided either through a formula or a figure. In the formula, Y represents the percentage reduction in design area and X is the ceiling height in feet. However, if the ceiling height is less than 10 feet, we must treat it as 10. As already mentioned, when the ceiling height exceeds 20 feet, no design area reduction is permitted. In other words, the reduction percentage becomes 0, and we must use the full design area specified in the NFPA 13 table. In the figure, the horizontal axis, or x-axis, represents the ceiling height in feet, while the vertical axis, or y-axis, shows the percentage reduction to the design area. To apply the figure, start by locating your ceiling height on the x-axis. From that point, draw a line upward parallel to the y-axis until it intersects the curve. Then, from the point of intersection, draw a line horizontally, parallel to the x-axis until it reaches the y-axis. The value you land on is the allowable reduction percentage for your design area. Now let's see how to apply both the formula and the figure to determine the design area reduction. In the first part of our design area video series titled Basic Concepts, we walked through an example and calculated the design area for a sprinkler system serving an ordinary hazard group 1 occupancy. Now, let's build on that example. Suppose the ceiling height in that project is 10 feet, and we're using quick response sprinklers. If all the conditions for design area reduction are met, such as wet pipe system, no large ceiling pockets, and no unprotected areas above cloud ceilings, we can apply the reduction. The first step is to determine the adjusted design area using either the formula or the figure provided in NFPA 13. By substituting 10 for X in the formula, we calculate Y, the design area reduction, as 40%. Using the figure and following the same procedure, we arrive at the same result, a 40% reduction. This means we're allowed to reduce 40% from the original design area of 1,500 square feet, which is specified in the table for ordinary hazard group 1. Applying the reduction, the final design area becomes 900 square feet. There's another way to calculate the final design area using percentage adjustments. When we want to reduce the area, we subtract the percentage from 1. For example, a 40% reduction means subtracting 0.4 from 1, which gives us 0.6. Then, we multiply that by the original design area, 1,500 square feet, to get the final value of 900 square feet. The total number of sprinklers within that area comes out to 7. Among these, the most remote branch line contains 3 sprinklers. When we compare the reduced design area achieved with quick response sprinklers to the standard response design area, we see a clear advantage. Quick response sprinklers activate earlier, helping contain the fire in a smaller area, resulting in less fire damage. This smaller design area also means the sprinkler system requires lower flow rates and pressure, allowing for smaller pipe diameters and a reduced water tank size. Altogether, these adjustments lead to a more efficient system and significantly lower installation and operational costs. As a final note in the design area adjustment for quick response sprinklers, the standard clearly states that the number of sprinklers in the design area shall never be fewer than 5. In NFPA 13, a sloped ceiling is defined as one with a pitch greater than 2 in 12. That is, a vertical rise of 2 units for every 12 units of horizontal run. This corresponds to a slope of approximately 16.7% or an angle of 9.46 degrees. When a fire starts beneath a sloped ceiling, the slope causes hot gases to travel toward the peak. This leads to heat accumulation near the highest point, often activating sprinklers farther from the fire source, while the sprinkler directly above the fire may activate with a delay. To compensate for the delayed sprinkler activation under sloped ceilings, NFPA 13 generally requires a 30% increase in the design area. However, the 2025 edition introduces 3 specific exceptions where this increase may not be necessary. The first exception involves installing a horizontal false ceiling beneath the slope. This ceiling must be capable of withstanding an uplift force of 3 pounds per square foot and must be supplemented with ceiling-level sprinklers. The second and third exceptions apply to obstructed construction with a slope not exceeding 4 in 12. In these cases, NFPA 13 provides specific criteria, either based on the depth and spacing of structural members or by requiring sprinklers to be installed in every channel. When the exceptions are not applicable, NFPA 13 requires a 30% increase to the design area values listed in the table. For example, in Extra Hazard Group 1 or 2, where the standard design area is 2,500 square feet, applying the 30% increase for sloped ceilings results in a final design area of 3,250 square feet. Just as we use multiplication to reduce the design area, a similar method applies when we need to increase it. In these cases, we simply add the percentage increase to 1, then multiply the result by the original design area. One of the key changes in the 2025 edition of NFPA 13 is the impact of ceiling height on the design area for sprinkler systems in ordinary hazard group 1 and 2 occupancies. According to this update, if the ceiling height exceeds 30 feet in OH1 or 40 feet in OH2, the design area must be increased by 30%. However, in OH2 occupancies with ceiling heights above 40 feet, this 30% increase may be omitted if extended coverage sprinklers with a minimum K factor of 25.2 are used. When a fire starts in a building protected by a dry pipe system, rising temperatures activate the sprinkler head. This causes the pressurized air or nitrogen used to keep the dry pipe valve closed to discharge from the piping network. As the pressure drops, the valve opens, allowing water to flow into the system, fill the pipes, and discharge through the activated sprinkler. This operation takes time and introduces a delay in system response, allowing the fire to spread and involve a larger area. To compensate for the delayed response inherent in dry pipe systems, NFPA 13 requires a 30% increase in the design area. This adjustment accounts for the additional time it takes for water to reach the activated sprinkler, helping ensure the system can effectively control a fire that may have spread further during that delay. In addition to dry pipe systems, NFPA 13 also requires a 30% increase in the design area for double interlock preaction systems in non-storage areas due to delayed water delivery. Furthermore, all types of preaction systems used in storage occupancies, whether non, single, or double interlock, must also apply the 30% design area increase. This ensures adequate fire control in environments where rapid fire growth and delayed water discharge pose greater risks. In extra hazard occupancies, the temperature of hot gases rising from a fire can exceed 1000 degrees Fahrenheit. When ordinary temperature sprinklers with a K factor of 8 or smaller are used, the initial activation near the fire and the resulting water spray reduce the temperature of the hot gases to a range between 160 and 280 degrees Fahrenheit. This level of heat, carried by the sealing jet, is still sufficient to activate sprinklers located farther from the fire source. Activation of these distant sprinklers increases the overall flow rate in the piping network. This elevated flow leads to greater pressure loss, reducing the available pressure at sprinklers near the fire. As a result, those critical sprinklers discharge less water, compromising fire control effectiveness. Based on these explanations, NFPA 13 permits a 25% reduction in the design area when specific sprinkler configurations are used to mitigate the risk of unnecessary sprinkler activation. This reduction is allowed when high-temperature sprinklers are installed or when sprinklers with a K factor of 11.2 or larger are used. These configurations help limit the activation of distant sprinklers and ensure more efficient water delivery to the sprinklers closest to the fire, thereby improving fire control performance in extra hazard occupancies. It should be noted that even after applying the 25% reduction permitted by NFPA 13, the final design area shall not be less than 2,000 square feet. Also, while NFPA 13 allows this reduction when either high-temperature sprinklers or sprinklers with a K factor of 11.2 or larger are installed, the reduction may only be applied once. Even if both conditions are met, the design area cannot be reduced twice. Sometimes, in designing fire sprinkler systems, it's necessary to apply more than one adjustment to the design area, such as increases for sloped ceilings and reductions for specific sprinkler types. According to NFPA 13, when multiple adjustments are required, they must be compounded based on the original design area selected from the table. This compounding method ensures a consistent and accurate outcome regardless of the order in which the adjustments are applied. It follows the commutative law of multiplication, meaning that whether you apply the increase first or the reduction first, the final result remains the same. For example, in an extra hazard occupancy with unobstructed construction and a sloped ceiling, if we use high-temperature sprinklers on a dry pipe system and the maximum ceiling height is 30 feet, we need to apply 2 increases and 1 reduction to the design area. Starting with a base area of 2,500 square feet, we multiply by 1.3 for the sloped ceiling, 1.3 again for the dry system, and then by 0.75 to account for the reduction allowed by using high-temperature sprinklers. The result is a final design area of 3,168.75 square feet. We also get the same result if we apply the reduction first, followed by the increase. Since the adjustments are compounded using multiplication, the final outcome remains unchanged regardless of the order.